All right, thanks a lot for the introduction and to Pierre for inviting me to give this presentation. In this presentation, the title says Fiber Optic Monitoring of Building Settlement and Bridge Degradation. There's a plus there because I'll discuss some other types of measurement we've done as well, but the focus really will be on fiber optics. At the outset, I'll say I've resisted putting any modeling in here, so we've done modeling for all the projects that I'm going to present, but I really want to focus on the fiber optic technology and what we can learn or what we can measure now that I think we couldn't measure before. So with each example, I'll try to give the motivation for why the monitoring is important, and then kind of a summary of how it was useful. One critical thing to say at the outset, some projects are more field experiments and others are actual structural health monitoring. There's a very big difference between those, and I think fiber optics gives us an opportunity in both of those areas. So 4 projects. The first 2 related to tunneling settlement, one at the building scale and one at the city or regional scale. Then 2 projects on rail bridges, one which is very much a field experiment, more on diagnostic of bridge behavior, and then a second one on rail bridge degradation. So the first project is related to a subway expansion in London. This was done mainly by the 2 postdocs shown here under my supervision, and we won some awards from this, which was nice. I should say at the outset, I spent 9 years at the University of Cambridge, so I didn't feel comfortable not adding Cambridge to the bottom of the title slide there. So most of this work is when I was there, although the interpretation has gone on since then. But this was a collaboration with London Underground and then some monitoring companies and funded by EPSRC. So the project was really to look at the expansion of this subway station. All the teal and the purple are new tunnels being excavated, and I'll focus on this St. Mary Abchurch building. We put monitoring in both of the buildings shown in yellow. But really this is the project. It's a very impressive, nice church designed by Christopher Wren, and the tunnel goes right under the corner of that bridge as shown in plan view on the right. And the question is really, how do we predict potential damage or cracking to that building due to the settlement process? So first, a few words on background. I spent a long time on this project in Cambridge looking at the effect of settlement on structures due to excavation. We did several centrifuge experiments on this. If you're interested, I could refer you to those papers. But essentially what's happened, here's the experiment. We build mini buildings in the centrifuge. We simulate contraction or settlement of the soil, and then we can measure in pretty good detail the deformation of the building itself. So it was good fun, but we learned a lot of things about the soil structure interaction problem. So if you have a building on the surface, I don't know, you can't see my pointer. On the bottom left, the green is the settlement profile under the building if you have no building there. So if with just the tunnel, that's what we measure in the lab. And then the blue is if you add the building, that's the deformation of the building. So current practice is often to just assume the green line represents the distortion of the building, in which case you're extremely conservative in predicting damage. So essentially, this ends up costing people a lot of money because you're very conservative and do a lot of mitigation measures to prevent this settlement process, when actually in many cases the buildings might be just fine. So the main mitigation measure is compensation grouting. Here's an old example from Westminster. Oh, my tunnels are offset. Those 2 tunnels were for the Jubilee line in London. They're going under the corner of Westminster. Essentially, the solution there was to pump a very large mat of grout into the ground beneath the building to prevent the effect on the building. And the way this is done is by boring a lot of shafts and then outward from those shafts radiating grout all over the ground, which is extremely expensive, difficult to control, and can cause heave of the buildings. So in this project, they really didn't want to do this process, but they couldn't tunnel under many buildings without ensuring that they weren't damaging them. So the question was, how can we measure in detail the actual damage to the building? And that's a big challenge, because what's typically done is a lot of point measurements from which we can get movements, rigid body movements, but not good measurements of deformation. So how do we do this in the field? So our project was to instrument this building, and this is a graphic demonstrating our instrumentation. So there's a cartoon of the the subway, and the building. All of the diamonds and the circles are traditional leveling or automated total station measurements. And the green lines represent fiber optic cables that we wrapped around the outside of the building so that we could measure strain in the building throughout the facade at 3 different levels, and then strain around the base of the dome of the structure. And the reason we want to do this, and this is the critical advantage of fiber optics, is that you can measure distributed strain quite well. We don't know exactly where the damage is going to happen, and so it enables us to predict, or not to predict, to measure damage a very wide range of areas within the building. How does this work? There's lots of different types of fiber optic sensing. You might be familiar. I'll give a very brief background, and I'm happy to talk more afterwards. We use fiber Bragg grading sensors. Essentially, you string a fiber optic cable, you attach an analyzer to the end, you shoot a pulse of light down that cable, and then you measure reflected properties of the light in order to determine or to measure strain in the cable. So based on the reflected properties, you can measure strain. Fiber Bragg grading works in a way that, as you see on the bottom right, you etch the fiber optic cable at a certain spacing. When you stretch that cable, the spacing of that etching changes. You can measure frequency change in the light, and you can get strain. So basically on one cable, as many etchings as you put is as many strain gauges as you have. So that enables you to use one cable to measure strain in a lot of places. So again, here's our installation. Here you can see the installation being placed. And here's a little bit better of a close-up. So in this case, since the building is there already, we clamped our cable at intervals of about 2 meters to the building. So we're getting strain measured, averaged over 2 meters all the way around the outside of the building. So our fiber optic installation was integrated directly into the contractor's real-time measurement system. So the nice thing about this is you're not expected to see any of this, but all of the left is their instrumentation system. All of the right is our fiber optic one, where they're getting kind of real-time strain measurements at basically 80 locations distributed around the building, and they have the trigger levels to make decisions or to implement mitigation measures if those strains were getting too large. So just a quick look at the data. When the first pilot tunnel comes through, this isn't all the data, it's a selection of it. This is plotted over about a year's worth of time. The pilot tunnel comes through and you see some increase in strain throughout the building. In the enlargement tunnel, you see quite a large increase of strain in some places, but all of the data down below is relatively distributed, and that's more or less elastic strain within the building. The 4 diversions to the top are the places where you get cracking. So one crack was existing. They had crack measurements already on it. The other ones were new ones that had formed that we could detect using this method. So if you go and look in detail, you see conditions like this where I've highlighted the cracks where we can see and pick this up. So the real benefit is that, again, you see it pretty quickly. You couldn't see it from the ground, so you know where to look. It targets your visual inspection, as I said, as well as it ensures for the owner as well as the contractor what's actually happening to the building. Now, the contractor doesn't always want that maybe level of detail, but it was specified in this case in the brief that this must be done, because when they did the analysis, they were predicting that there could be more damage. So they said, well, if you want to do this without any other mitigation measures, you have to show that no damage is occurring. Okay, so that was the first project. Very briefly, a second project, which doesn't use fiber optics at all, but looks at measurement of building deformation at the city scale. This project was on Crossrail in London, and I have to credit Georgia Giardina, who is a postdoc with me, who led most of this work. And also this was a collaboration with JPL. We had a nice presentation yesterday from JPL looking at regional movements of the ground, but it's really impressive, I think, what we can now do at the building level with this INSAR technology. So this is using satellites, INSAR radar, to look at the ground settlement due to the Crossrail tunnel. So here's the tunnel line is shown in red. It was twin tunnels, elevation on the top. So basically all the way across the city of London, 1,300 buildings needed to be assessed for the settlement effects on those buildings. Many of those buildings were instrumented, but not all. So our question was, can we go back afterwards without any monitoring data and evaluate building deformations using satellite? So the image on the left shows a map which is created by taking satellite images before and after the tunneling process. You clearly see the tunneling route, which is in red, going through the city, a close-up shown on the right. And again, the red is representing roughly 30 millimeters of vertical displacement. The question is, as the last speaker, or 2 speakers ago said, maybe the absolute settlement doesn't matter so much, but the differential settlement is what we want to know. So can we actually use this to measure differential settlement or building distortion? And that's where you're getting right at the limits of the ability of the technology. So here you see 6 case study buildings where we took all of the points where we could get what's called persistent scatter measurements, so points where the equivalent points could be recognized in consecutive satellite images. And this is the level of data we get. So I tried to put some black curves through the black dots, which may or may not convince you in any way at all. But I think it was a kind of a groundbreaking study to say, these are only maximum settlements of between 5 and 15 millimeters measured from satellite. So if you're above that level, if you're in the 15 millimeter range, we can do that. We can get building deformation, which we could use to back calculate maybe maximum strains potentially from satellite data. All right, shifting gears a little bit. This was a third project on what I'll call bridge diagnostics. So this was also conducted with the Cambridge Center for Smart Infrastructure in Cambridge, where I was working, and was a collaboration very much with AECOM and Network Rail. Network Rail manages all the rail infrastructure in the UK. It was also funded by the Alan Turing Institute. They're doing a lot of data science on the data we've collected, but I don't have time to show any of those results. So again, I'll just focus on the installation. This one's ongoing, and it's by a current PhD student, Sam Cocking, who's working with me on this project. So for me, this presents an interesting question from a structural engineering point of view, as well as from a bridge degradation point of view. So in this project, we're looking at a bridge which carries rail traffic. The bridge needs to last another 5 to 10 years. So they'll do an upgrade on the line in 5 to 10 years. So there's a very specific requirement by the owner to say, can we ensure that we have a safe bridge and we don't need to do work for that amount of time? The current method of evaluating the bridge is to use deflection measurement, which is shown on the right. When you do this deflection measurement, you need a 38-mile diversion because it's a rather remote bridge. So the cost of that alone practically justifies any one amount of monitoring you could do to eliminate having to do that every 6 months or 4 months, which is the current scheme that they need to do. So the bridge is notably damaged. So it has 2 external walls, spandrel walls on the outside. Just inside of those, so on the left, you can kind of see them. There's cracks which separate the barrel of the bridge from the 2 walls on either side. And it turns out that that barrel of the bridge actually pumps back and forth inside those walls when that separation becomes too big. So at the point before they did the mitigation, that pumping was visible when you stood under the bridge. So they did mitigation and they want to understand how that worked and how effective that was. So they've currently stitched all the external stones back into the main part of the bridge. They've stitched those together and grouted them in. But it's well known that that doesn't last very long because of the stiffness, the differential stiffness problem you have. So they know it's going to start pumping again, and that's one of the things we want to measure. My side interest in the project, which I convinced them to fund us to do anyways, was to understand a bit about the behavior of these bridges. So there's a debate as to how these bridges behave. Many people say the abutments are way stiffer, and all of the bridge spans directly in the skew direction to the abutments. Many other people say, well, the spandrel walls are stiff, lots of the load goes to the spandrel walls, or the bridges span square, so the load goes something on the right. So we also wanted to answer this question, and so I thought we came up with a reasonably novel idea, although it's used all the time in strain gauges. But we just did basically fiber optic rosettes underneath the bridge to allow us to measure principal direction of stresses and flows, so forces in the structure, by stringing a lot of fiber optic cables. So the triangles is a plan view of the bridge. The triangles are 2 rows of triangles represent the fiber optic system. AECOM, the contractor, put in a lot of other traditional techniques so we could compare and validate the accuracy of our data. I'll skip this here. So there you see the example installation. So we can string the fibers, curl them around, string them through. So you're clamping and stringing. That process is a bit intensive. The nice thing is then you leave the installation there and it's fairly durable. So this is meant to last. Well, the other nice thing is that the fiber optic cable itself, again, is very durable. You can update the analyzer, which you connect to the end of the fiber very easily by accessing the cabinet, changing out the analyzer. So in that sense, the long-term ability to measure things is quite unique and efficient. So there's a picture on the left of the fiber optic cables installed. And just really quickly, a very simple diagram. The red represents tension and the blue compression in these principal stress vectors on the right. And you can get very nicely the flow of forces through the bridge dynamically as the train goes across. I should say the other nice thing about FPGs is you can measure at a kilohertz. So at 80 or 100 locations, you're getting a kilohertz of strain data at every location. So you can do dynamic measurement quite reliably and quite effectively. We can monitor other things like crack opening. We compared it to traditional methods and got good accuracy. We've produced a couple of practical documents for the UK, which is some recommendations for how they might monitor bridges using this technology as well as others to do across their route. So just before I finish, I'll make one comment on long-term monitoring. I won't explain this whole project, but it relates to something the last speaker said on you've got to monitor for a long time, several seasons, to actually know what you're measuring. And in this case, this was another bridge. It was a viaduct as shown here. It was very badly damaged, so lots of cracks all over the place. They don't know which of these cracks are active. Many of them have been around for 10, 20, 40 years. And so, again, using distributed sensing is very useful because you can capture all kinds of crack locations, all kinds of locations of potential damage very effectively. And I'll just skip to the results. Again, there's the installation. Oh, I should say, I didn't say before, this is all powered by solar panel, and the system is triggered by the train as it comes across, so it turns on, takes 10 seconds of data while the train comes across, turns off, and transmit that data to us so we can do all the analysis remotely. Here's an example where we are able to pick up localized damage quite early. And in relation to other methods, one other benefit of this is there's a big difference between detecting global changes and local changes due to damage. So when you get local damage, it doesn't always manifest itself in global measurements. So if you're doing accelerometer measurements, looking at mode shapes, oftentimes you don't pick up the damage until you have a huge amount, whereas in this way you pick it up quite early. And so this is just a graphic to show there's a huge seasonal effect. The whole bridge breathes in and out every year, and that seasonal effect is demonstrated all around, but you can see localized damage quite clearly in some places with respect to that seasonal effect. So I'll skip the conclusions. I will say one thing we're working on now is embedding fibers in concrete. So we're doing a lot to understand strain distributions in concrete under large loadings. And I think with that, I'll acknowledge numerous supporters of this work and thank you for your time.